refers to Planck scale, the scale of gravitational forces, gravitational force. And the electroweak scale, here I wrote it by IR scale, but it doesn't matter, IR or electroweak scale, is something just about the Higgs boson mass, some by an order of magnitude, and it is given by unitarity arguments. Okay? And on the other hand, your ultraviolet scale is something close to Planck scale or string scale, whatever. And there are two fundamental questions, or there are two fundamental problems we have with these scales. One is that we want to, or we have to generate these two scales to have this hierarchy. Okay? I mean, it doesn't need to be the realistic scale, but given a two-scale theory, just imagine like that. It doesn't need to be the real electroweak scale. Okay, one is that we have to generate hierarchy. For example, in the realistic case of electroweak theory, this ratio is something like 10 to minus 15. And we have to generate this number. We have to drive, or we have to understand why this scale, where this scale is coming from, why it takes this specific value. For example, in extra-dimensional theories, argument was the following. They said that electroweak scale is the fundamental scale, and depending on the number of extra dimensions and depending on the geometry and blah blah structure of the extra dimensional space, they have derived Planck scale. So they have produced this hierarchy. They said that this hierarchy is coming from this origin. So that's okay. And the second question is to stabilize this hierarchy, this ratio, because this ratio is not stable under quantum mechanical effects. That's the fundamental problem we are having. So hierarchy problem has two versions. One is the generation of the hierarchy. The other one is the stabilization of the hierarchy. There are two problems. Usually, people working in supersymmetry, for example, speak only on the second problem because they don't know how to generate this scale. They only speak about its stabilization. And they say that this ratio is given by, for example, scalar superparticle masses in the game. For example, spark mass or gluino mass. And no, let us discuss the known problem, this problem itself, in a simple framework. This is not something new, this is the known problem. I am putting gravity in the game because I will use it later on. Otherwise, you don't need gravity at all, okay? You don't have to have such a thing in the game. But in any case, suppose, let us consider a single real scalar field I interacting with Einstein's gravity. Okay? I mean, there is nothing fancy. You don't introduce some extra dimensional structure, you don't introduce some fancy gravitational theory, you don't introduce anything. You have Einstein's theory, where this scalar field is coupled to this Einstein field. G is metric tensor here, G. R of G is the curvature scalar. Just to remind you the story, this zeta C is conformal coupling, it is 1/6. And this is enforced upon us because we have to have a renormalizable theory. If this coupling is different than 1/6, then we don't have a renormalizable theory for scalar field. So we have to have this coupling as 1/6, and it's conformal like. And this is Planck's constant, it is inversely Newton's constant, as we all know, and everything is fixed. Here, the scalar potential has this standard form. It has the vacuum energy V0, it has the mass term and pi squared, and it has a particle coupling of this sort. And we say that M5 is much less than M prime. And we take it granted, because we don't know this. We don't know how to generate this. We say that this is smaller than this. Okay? If these two scales are close to each other, we don't have any problem. We have problems just because there is a hierarchy splitting between these two scales. That is the crazy thing. I mean, if weak interactions were happening at the scale of around the gravitational scale and Planck, then we wouldn't have any problem of naturalness, and diurnation would be at a single scale and Planck. But we have electroweak interactions at a much less smaller scale than the others. Okay, now let us compute quantum corrections. Calculating quantum corrections means we have to take into account fluctuations of this theory, of fields. Here, our field is scalar field, and scalar field has, we are trying to construct a Wilsonian effective field theory at the scale lambda IR, so there is a there is a long wavelength, slow field part here, and there is a fast part, or small wavelength part here. This part has large amplitude and long wavelength, like this, and this part has small amplitude yet high frequency, like this. And this is known as quantum fluctuation. This is known as classical field. Actually, near the minimum of the energy, this phi is actually a constant. And closer to the minimum, closer to the value that minimizes the potential, your field is almost constant. In our calculations, as we usually do in effective field theory calculations, we take phi constant, we deal with delta phi. Actually, phi is not constant, but it's a slow varying phi. The other part is a fast varying part. And this is the idea of kinetic. This is how we construct effective field theories. Essentially, we are summing up all high energy modes to calculate to obtain an effective theory at a given scale, so that our coefficients encode high energy effects, but our operators encode low energy effects. This is the famous operator product expansion in QCD. Okay, so to do it, I have to integrate this fancy path integral. I have to sum all the scalar field configurations, but I separate slow varying part and fast varying part. And in the fast varying part, I have this extra piece coming from the quadratic part. And this is the classical part, which depends not on the big phi, but small little phi. That is, the little phi is the slow part. So I have to do this Gaussian integration. It can be done easily to obtain an effective action that depends on metric G and scalar field phi. And this effective action has this slow varying classical part, classical action, and this quantum correction. Quantum correction has this form. Leaving aside the finite parts, quantum correction has a part which depends fourth power of ultraviolet scale, which involves the second power of ultraviolet scale, and which involves a logarithmic piece in the game. And this is the usual story. If you add these two pieces and write your theory in the normalized version as a normalized field theory, it's a normalized field theory. Therefore, we have to put all these additional corrections in the redefinitions of the couplings. It means the normalizability. Okay, so, and indeed our parameters are normalized. The quartic coupling renormalizes logarithmically, as you see here. The mass square is normalized in this fashion. It has a logarithmic piece and a quadratic piece. And the vacuum energy is normalized to have quartic contribution, quadratic contribution, and logarithmic contribution. So essentially, what's happening is that, I mean, just to emphasize, this term kills us. Because this term, you remember, lambda UV is close to the Planck scale. That's the highest possible energy scale in the game. This means that after normalization, scalar field obtains a mass square around the Planck scale, up to within a loop factor. At one loop, within a loop factor. Such a crazy big thing. On the other hand, vacuum energy, again, is pushed towards the scale of the Planck scale. It obtains a huge vacuum energy. This is, people mostly call this thing cosmological constant problem, and this thing is the mass hierarchy problem. Okay, mass hierarchy. There is a mass hierarchy. As you see, these two divergences just kill the system. And you can imagine many things. I mean, you want to solve this problem. You want to stabilize your theory. As you see, since m pi squared is getting such a large correction, since lambda IR must be above m pi, this means that your IR scale is now at the Planck scale. And this means that your hierarchy is gone. It has become a degeneracy. Hierarchy is killed. It is washed out, and you get to a degeneracy, as you see here. Originally, they had m pi much less than m Planck. After normalization, we find that m pi is just around m Planck, within a loop factor. So our theory is dead. Nothing is left over. scalar field, the conclusion is that scalar field is not natural. That is to say, it cannot preserve its scale. Under quantum effects, when you add effects of quantum fluctuations of fields, the scalar field gets crazy and it goes to a very high scale, and you see, the story is this. This is just this. No, we can look for the reason. Huh? Actually, the pretext of let's look at the quadratic correction. Okay? I mean, for example, for quadratic contribution, there is no constant multiplying lambda u into 4. This means that you can never solve this thing. You can never play or change this thing. By changing your couplings or something, you cannot change this thing. This is always divergent. You cannot kill it. It is there. But when we look at the quadratic divergence, we see that it has quadratic coupling in front. It is sensitive to quadratic coupling. It is sensitive to model parameters. But the vacuum energy is not sensitive to model parameters, at least the quadratic part. It is just there, and you can do nothing about it. It is just there, and it is insensitive to your model parameters. It is just sensitive to fermion-boson balance in your system. If the number of bosons are equal to the number of fermions, then you kill vacuum energy contribution. Otherwise, no way out. Or your gravitational theory must be modified.
If the number of the fermions and boson pieces are equal,
then this term is...
Could they have different masses? Not degenerate?
They have different masses, but the mass difference will affect this.
Well, you may have a violently broken supersymmetry, so the masses would be different, but once you have that supersymmetry, which could be realized at higher energies, you could get rid of the vacuum energy.
But these contributions will be over there.
Or the quartic one.
Also, for cosmological constant problem, these terms are huge. I mean, forget these terms. For example, even a contribution of the order of neutrino mass to 4th power gives a huge contribution. Actually, electron mass to 4th power gives a huge contribution. The only allowed contribution has the size neutrino mass to 4th power. Neutrino rest energy per cubic volume defined by neutrino quantum wavelength is the amount allowed. No other amount is allowed. That's the most we can do in cosmological constant. Okay, this is this. Now let's look at it. The pretext of and the reason for this divergence is lambda phi to phi to 4. It is this term. I mean, when you look at the quadratic contribution, quadratic divergence, it is this term which is creating the problem. Because quadratic divergences are proportional to lambda phi, the quadratic coupling. Well, what can we do with this? For example, supersymmetry introduces some new fields side by side with such specific couplings, square root of lambda phi times phi squared side by side, such that roots of fermions cancel roots of the scalar fields phi, so they are equal to each other and they just cancel each other at one loop level. So you don't have such a crazy dependence on the ultraviolet scale. You kill it. So it's good. In extra-dimensional theories, lambda UV is not these divergences are not a problem because lambda UV is just at the electroweak scale. It's at the lambda IR. So you don't go upwards. I mean, it's just already there. And so you never have any big correction because your ultraviolet scale is right at the scale where there are continuous correction, essentially, within an order of magnitude or so. So this is this. Well, you can look at it, huh? You can check it out. You can see, you can try to see if there is any other way, because essentially, always the conclusion is that at least in the present epoch of experimental search, the particles, there is no new particle other than this itself. Huh? So we don't have any particle that can fit to supersymmetry or extra dimension or another theory. We don't have it. But that's why we have a problem with naturalism. The nature seems unnatural. So let us ask a third question. Let us look for some third way. Okay, it's not technical. Technical is already done because we have fundamental physics. Okay? So it's out of discussion. So Can we have another way? Can we have another argument, another thing to argue for? What we have to use what we have at hand. Huh? We cannot use some fancy thing because the nature experiment killed all fancy things. We cannot add something extra. We cannot put some extra particle. They don't exist at all. But when you look at this particle interaction, you can say that, well, I can just take lambda pi equal to 0. No problem. No problem. No, it just kills you because lambda pi 0 means your vacuum expectation value is crazy big. Your field is on a flat direction and it rolls to infinity. So it is forbidden. Your potential must have a well-defined concave structure so that you have. And essentially, let's think about one can imagine doing some game, playing some game, such that this quantic interaction is somehow replaced by some constant amount of energy. That is to say, the quantic interaction is there, but you, in essence, you shut it off. You make it off by saying that my field doesn't have such a quantic copy. Can you do it? Well, you can do it. Is it a solution? We don't know. We should check. Okay. The way, of course, by hand you can go there and write instead of phi sum MC. It's not the thing we are doing. It is simple to do. You cannot replace a field with a scalar. I'm sorry, the constant. Here, this MC is a new scale, and essentially, what's happening is that if you were doing a normal conformal transformation in the theory, in the transformed frame, your theory would have a conformal invariance. And this scale MC, what it does is to break conformal invariance in that scale, in that frame. Since conformal invariance is already broken below Planck's scale, MC cannot be below MC. I'm sorry, below M Planck. But eventually you will see that nothing will depend on MC. MC is just a H parameter in the system. Nothing will involve MC. MC, things will be independent of MC. So just, it is some parameter right now. We can make this replacement of this particle interaction with such a structure by using a conformal transformation. But not an arbitrary transformation, not some fancy transformation. The transformation has a conformal parameter, conformal transformation parameter, which is itself given by the scalar field itself. This is not something ordinary. This is not something you would find in a book, okay? It is not given, normally when you do a conformal transformation, you write your old metric, this is old metric tensor, this is new metric tensor, you write some scalar function squared here, that's okay. You go ahead. You don't know the scalar function, scalar field there. That is known as conformal factor. Conformal factor enters into system as an additional scalar field. It's a new degree of freedom in the game. And so your system is modified actually. But when you do it in this way, you don't change your system. Your system involves the same number of fields as before, because your conformal factor involves only the scalar field itself, nothing else. So when you play with this game, you see that the original. I'm sorry. This Lagrangian goes through, this action goes through this one. As you see, the gravitational part is again similar to the original part. Okay, some quadratic interaction, there is this coupling between these. There is a new scalar field, the phi tilde. This phi tilde is given in terms of the old field in this way. As you see, the old field is redefined to have a canonical scale. The new field has certain properties. For example, its mass square is proportional to m pi squared. But with a new factor involving mc squared over m pi squared. Next thing is that its quartic interaction is determined by the vacuum energy. And as I promised before, the quartic interaction in the previous theory has become vacuum energy in the new theory. This has become vacuum energy. No, lambda phi is gone. No, in the end result, we will see that no divergence can depend on lambda phi. Impossible to be lambda phi, because lambda phi is shut off now. Lambda phi does not mediate any interaction now. So, this is the story. This new field is a canonical scalar, but there is a big difference here. The new scalar is a ghost, actually, right? Is a ghost. Tilde is a ghost. It's not a real scalar, but this is expected because this is gravitation. In gravitation, gravitational scalars are always ghost fields. That is by definition. Even dilaton coming from string theory is a ghost field. It must be ghost. It is ghost, always ghost. We have to live with this. Okay, that's the ghost. Okay, let's continue. Ghost is not a ground for us. We can calculate quantum corrections as we Let us try to compute quantum corrections again. As I did in the previous frame, I have to divide my fields into slow part and test part. As I did before, it's the usual division. But you see, my IR scale and UV scale are not modified. They are new scales. Why? Because they were fixed scales in the previous frame. Now I made a conformal transformation. All fixed scales are transformed because fixed scale means P mu equaling n squared. And momenta are now modified because metric tensor is modified. Therefore, you have new scales, lambda IR tilde squared and UV tilde squared. It's given in terms of these. Did you see? They know in more fields than the field itself. This is a must actually. You cannot escape from it. Because lambda IR and lambda UV means they are momentum cutoffs. And in that frame, your momentum P squared is cut at lambda IR and lambda UV in this spectrum. And now you made a transformation on your metric tensor. This means that your cutoffs are modified also. Cutoff scales.
Do all scales turn into fields by conformal transformation? Or only
No, only this, because this is P mu. This is the measurable scale, cutoff.
The thresholds now, lambda are not dynamic.
Essentially dynamic, but I'm performing an effective field theory calculation with a slow field. We can imagine this pi as a constant thing. We can go and continue with that. It's not a problem. But actually, it's becoming a dynamical thing, yes.
Are the cutoffs becoming dynamical in that case? You mean this?
Wow, should I say dynamical? Not actually dynamical. Normally, you can replace these cutoffs with an average of the fields, okay? You can always do it, essentially.
I would ask something related to this. So that conformal transformation indeed turns the cutoffs somehow, let's say, position dependent.
Field dependent.
Field dependent.
Field dependent. And that's the thing, you see, in relativistic field theory, we are never able to kill all these divergences. And we always put a hard cutoff on momenta. This is saying that the cutoff on the momenta are not necessarily hard. They can actually be made field dependent. Once you do that, you have no freedom. You will see.
So when calculating a certain transition amplitude, for example, do we use the average values of the fields for the cutoffs? I mean momentum integrals. For example, when we want to calculate a matrix element, we need to compute a momentum integral. And,
yes. Your momentum. This is a very, let's say this is a toy model, which just a single scalar field. I didn't discuss it for a general fields, etc. But this is the fundamental thing. Your IR and UV scales will slide with the field. Which field? With the scalar, not with other fields. With the scalar. That is good. You see, you will see. That will be good. That will, in a sense, hard momentum cutoffs are replaced by soft momentum cutoffs. Essentially. It is telling us something. Now, let us do the original integral is this. I am calculating this correction. So I transform this quantum mechanical amplitude to this new frame. This transformation is one-to-one. This is identity. There is identity. This is identity. I mean, there is no anomaly in this transformation. That's the good thing. I'm changing metric tensor. At the same time, I'm changing scalar field. There are two changes cancel each other. So from the determinant in the path integral measure, I don't have any anomaly coming out. So this means that this theory is identical to this theory. That's the thing we are using. We are using an identity. This theory is equal to this theory. It's an identity, and we are going on our path. And we have to do this integration, we are dividing it again into slow and fast parts, as you see. Here, the fast part, the oscillating pump fluctuation has got a mass parameter. Now, mass parameter is similar to the original one, but it involves these extra factors in the game. Particularly, when you look at it, you see that the particle coupling is now determined by vacuum energy, not by another thing. That's important. And when you do this integration, we obtain such a result, which is the usual standard result, as in the previous frame, the same result. And again, our action is divided into two in such a way, and the correction term, as in the previous frame, has this form. As you see, lambda u to fourth power, lambda u squared, and 5 to the squared. But here, lambda u squared, lambda r squared. We don't have theta because that's a ratio. And as you see, when you look at these things, in this frame, you see that there are no power law divergences. In this frame, not in the other frame. We will go back to the other frame now. But in this frame, when you look at it, we don't have any power law divergences. Why? Because our scales themselves are depend on fields, and you cannot find any parameter that can diverge together with the UV scale. The reason is that UV scale is always divided by NC squared, because NC squared is a high scale, and you divide it by NC squared every time. Anyways, when we go back to the other frame, the things will be much more transparent. And when we go back to the other frame, we will find that our parameters are renormalized again, as in the previous frame. But the renormalization is different. For example, particle coupling is renormalized in this fashion. As you see, it is additive, and the correction, first of all, let's look at the corrections. The corrections do not involve lambda phi anyway, because the Q affects all lambda phi. The Q affects all quartic coupling. So no correction involves anything about the quartic coupling. So we have somehow aimed that crazy problematic coupling. So that's good. Secondly, lambda phi bar is renormalized logarithmically and additively, as you see. But the correction is crazy small. If this hierarchy is large, then this term is crazy small, and the effect is almost nothing. Let's look at the renormalization of the mass square. When we look at this expression, we see that it is first of all multiplicative renormalization. This means that its renormalization is the same as quark mass renormalization or vector boson renormalization. Just the same structure. This means that if m pi squared is small, then m pi bar squared is also small. That is good. Why is this renormalizing in a multiplicative fashion? Because I am in a frame determined by conformal transformations, and there is a hidden conformal invariance background at the ML. And it is that hidden symmetry that preserves, that somehow conserves the symmetry, the variation of the mass. But let's look at the parentheses. In upper there is a 1 coming from the level, and there is this loop factor, and in the parentheses. You see, we have quadratic contribution, huh? Lambda u e squared over m Planck squared. We had the same correction in the previous case, but in that case, we did not have m pi squared in front, and this was an extra factor. As you see, the thing is that this lambda u e squared is at most m Planck squared, because m Planck is the ultimate ultraviolet bound. Lambda u e never exceeds this thing. Therefore, this correction is a very small correction. Actually, this is the smallest correction here. It is not the largest one, smallest one now. And the next one is the logarithmic correction, and as you see, it involves the vacuum energy of the other frame. Vacuum energy. Its correction involves the vacuum energy in the other frame, not the quartic coupling here, because vacuum energy dictates or determines quartic coupling in this frame. And when we look at this correction here, overall correction, this term is negative. That's to say, m pi squared decreases with the loop corrections. That will be important for us. It will tell us something. Second thing is that, well, as you see, the correction is small, of course. It is natural. You know, the scalar doesn't get a crazy big mass squared term. But let's look at this vacuum energy. has a multiplicative piece. The third level part is already multiplicative, of course. This part is multiplicative, but there is a quartic part. Quartic part is there, and it is still divergent, and it is huge divergence. It is the same divergence we had in the previous frame. Why? Because quartic divergence cannot be prevented by using, by changing quartic interaction. It is there, and it cannot be changed by, it is there, and it doesn't depend on parameters in the Lagrangian. It is always there. So by changing frame, you cannot change it. You cannot play it. It's always there. So divergence is there, divergence. And when we look at this overall result, we see that they do not depend on MC, the parameter MC. The mass scale MC. You remember I introduced a scale MC to replace this quartic interaction with some constant energy amount of energy. And it is no problem. Because it's just like a gauge parameter. You cannot have any dependence on that parameter. This means that this going to other frame, calculating corrections that are coming back is a physical thing. Otherwise, we would have a dependence on the fancy parameter NC. We don't have that dependence. That's why we have these results. It involves only the ultraviolet scale, it involves only the IR scale given by the scale as mass, and it is this.
What you have done here is you have calculated the correction in another scale and then you have transformed that.
Yes, that's the best point. That's the point. In a sense, I'm using gravitational frame freedom as a renormalization bar to renormalize the scalar at hand. Just game. It is essentially when you look at the system, you don't have any other freedom. That's the only freedom. Anyways, one can have some other idea. Okay. Now, let's look at a critical aspect of the structure. It is actually interesting. Let's look at it. First of all, let's look at the constraints on the system. If I go back and see the structure here, as you see, my field's quartic coupling is this in this frame. This quartic coupling should be positive, and this quartic coupling should be less than 1 for this theory to be perturbative. Otherwise, there is no meaning of any calculation. I cannot expand it in loops. Then the second loop will be much larger than the first loop. It will be crazy. Therefore, if you use that constraint, I find that the vacuum energy must be in this range. It is larger than 0. It is positive as we measure in the nature. And its maximum value is 9 times m prime to 4. Of course, it's super blanking in this sense. Okay? It's taking a large value. It is always possible because vacuum energy has got always a primordial contribution. It is never under control, and you can never say anything about it. It is just a constraint you find when you form a physical constraint. Next thing is that, since you see, let's go back here. Let's go back here. As you see, the renormalization is multiplicative, and this part is negative. This means that with respect to the 3-level mass square, your normalized mass square can have opposite signs. They can have the same sign. They can have the opposite sign. Same sign is meaningless. I mean, you can discuss it, but it doesn't lead to. It doesn't give you any interesting thing. First of all, if they keep having the same sign, you lose hierarchy. You cannot create a hierarchy. But if they are opposite in sign, if they are opposite in sign, m5 bar squared or m5 squared less than 0, this requires B0 to be larger than this factor. Okay? From the quantum correction level. And this thing means that lambda IR must be less than lambda UV by this factor. Lambda e to power of minus 4 over 3 pi squared. This ratio is model independent. It has nothing to do with anything. Okay? It's just a simple scalar theory. Come on. There is nothing. There is no gauge symmetry. There is nothing in the gauge. But this factor is important. You see, this factor is 13. 4 over 3 pi squared is 13. E to power of minus 13 means 13 E foldings. 13 E folding of lambda UV means 100 TeV. This means that your IR scale is we have created a hierarchy because IR scale is bound to be less than an upper bound, 100 TeV. We have created hierarchy. Also, we have stabilized hierarchy because m pi squared, this ratio is always all the order of 1. It never, there's no decorrelation. So you see, we have started with the generic scalar theory in a gravitating background, in a curved background. Nothing special in the game. By using this technique of renormalization, by using this renormalization approach, we are able to naturalize the scalar, such that scalar's mass is required to be less than an upper bound. And this it is interesting that this upper bound is 100 TeV, 100 TeV. 100 TeV is just a weak scale. I mean, it is not much less than 1 TeV. All it says is that it is less than 100 TeV. It could be 10 TeV, 1 TeV, 0.5 TeV. It is saying that you are to be at the TeV scale. You see, TeV scale is coming from essentially nothing. It is coming from the inner consistency of the model. Another point is that imagine a gauge theory. Suppose you are at the tree level and you have exact gauge invariance. Your gauge invariance is exact. There's nothing special. So symmetry is not broken. Imagine standard model. Symmetry is not broken at tree level. You compute radiative corrections. And as you see, scalar's mass can change its sign under radiative corrections. This means that it is radiative corrections themselves that breaks the gauge symmetry. So gauge symmetry breaking is under control because it is the radiative corrections that break your gauge symmetry to induce such a scale. It is this. And then, of course, you can calculate vacuum expectation by your scalar. At the tree level, m pi is squared. Let us suppose that at the tree level, m pi squared is positive. Then the vacuum expectation value of phi is 0. You cannot have anything because potential is minimized at the minimum, at the origin. But at the loop level, your m pi squared is now negative. It has changed sign. So we have a vacuum expectation value in the game. And you can calculate it easily. Minus m pi squared for lambda phi, and this is approximately m pi squared lambda phi. This means that you stabilize your scale, your system. The scalar theory is stabilized at the scale near its tree-level configuration, such that scalar field cannot take the mass of the scalar field cannot take any arbitrary value. It has to have a mass less than 100 TeV. That's all I'm saying. Thank you.
You said that technical is now out of